Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture on control systems. Over the last few lectures we've been focusing a bit on this e to the at matrix, this matrix exponential, right, and we've seen that it plays a pivotal role in allowing us or enabling us to obtain the solution of the state space equation, which is essentially the solution of the differential equation, right. So we've seen around at least three methods. The first method being that you have this matrix A, you take Si minus A inverse and then take the Laplace inverse of that matrix entry wise, yeah, and you get the exponential matrix. The second method was tantamount to either diagonalizing it or getting it to its block Jordan form, right, and then we saw that whether it's a diagonal matrix or it's a block Jordan form matrix, obtaining the matrix exponential is simplified, yeah, in either case. And finally we saw that by cleverly using this Cayley-Hamilton theorem, which says that the characteristic polynomial of a matrix is such that when you pass the matrix as an argument of the characteristic polynomial, then it vanishes, right. So we've seen these three methods, and I thought that today I should actually start with, for one lecture at least, a brief digression into linear time varying systems, just to impress upon you the fact that here is something which we couldn't have addressed using the conventional Laplace transform tool that we have familiarized ourselves with when we were dealing with this classical control techniques. But before that I thought there's something more important that I should probably highlight a bit, because in theory I have told you how to obtain the solution of a state space system of equations, but then at the undergraduate level you will be required to solve a number of problems numerically, whether aided or unaided by MATLAB or not, right. Sometimes we give these simple 3x3 systems and we expect you to be able to solve for them at least by hand computation to the extent possible, right. So I thought I should take an example, and just to show you that it's okay, in principle you understand how to do it, but still it requires a good bit of practice actually to do this quickly by hand computation, yeah, unless you have the access to a computer. It may not be such an easy task unless you practice this well enough. So we'll take an example and let's see how far we can get with that, and in the process we'll also learn a bit of more details about this Jordan form and its matrix exponential, and something that we haven't talked about is basically these complex eigenvalues. How do we deal with such cases? If you remember, we've only focused on real eigenvalues, whether they're repeated or not. If they're repeated, then there's this possibility of Jordan canonical form instead of the diagonal form, yeah, which we obtain through similarity transformation. The other point, maybe I should make a brief mention of this, maybe a couple of lectures back we discussed this similarity transformation, right, and we drew this diagram where we had this, okay, let me draw that again, maybe not the entire one but a brief version thereof. So we had this ODE or the transfer function given to us. By now we know from a classical control knowledge that going from an ODE to a transfer function and the other way around is straightforward. So from here we saw that we can get to these several state space realizations, right, SSR to so on and so forth, and we can also go back, yeah, we saw that. So this realization, this is basically a realization, and going back here we basically take the C times Si minus A inverse B plus D, yeah, that's all there is to it. Now notice that we also talked about going from one state space realization to another through this similarity transformation, and we saw that it goes both ways, right, yeah. So we actually saw this quite clearly and quite explicitly the other day, in the other lecture. But one point which I think needs a bit of a mention here is that, look, what we have shown is that if you generate multiple state space realizations from a given state space realization through similarity transform, then from each of them, due to the invariance property we proved, you can independently go back to the same ODE or the same transfer function, right? But from the same transfer function, so if you go the other way, from the same ODE or the transfer function, if you come to different state space realizations, there is absolutely no guarantee that you will always have some similarity transformation that allows you to go from one to the other. Unless they are all generated by a single similarity transformation, yeah, there is a connection between them. This is not always true, yeah, that you can always go from any state space realization of an ODE or a transfer function to any other. Yeah. So suppose I realize it in one form sitting here, you realize it in some other form sitting at home, yeah, there would be some restrictions subject to which there will exist a similarity transformation between your realization and my realization, okay, and those restrictions have to do with whether there is pole zero cancellation or not, yeah, in a sense about controllability and observability. I think we have spoken a bit about this earlier also, but I think this statement is very important. So you do not waste your time searching for similarity transformations between any two arbitrary state space realizations of a transfer function, yeah. Know well that this is not always possible, okay. So that is one point I wanted to put across. So enough of a bit of a digression for today. Let us quickly get into what we had planned right at the beginning of this lecture, which is to take an example, yeah, and I will not take one of the simpler examples, I will take one of those examples where we actually encountered this Jordan form, yeah. So at one go we will see several things and we learn why even though the Jordan form is not as good as the diagonal form, it is almost there, yeah, almost as good. So we already are familiar with one of these matrices, so I will take that particular A matrix which we have already seen the Jordan form for, yeah, so that I do not have to find that similarity transformation again afresh, right. So let us take the state space system given by this. Let us take the example we took the other day, 1 1 2 0 1 3 0 0 2. So if you recall, this is exactly the same matrix that we had taken the other day, okay, and let us say this is 5 3 1 times u, yeah, a perfectly valid state space representation, and let us say y is equal to 1 0 0 x, alright. So we shall see that given that this x of 0, which is going to be a 3 tuple of numbers, so this is 2 0 1, and u is just the step, unit step, okay. So the question asks us to solve for xt, hence obtain yt, right. So of course you understand this pretty well enough that once you have solved for xt, this part of the question is really trivial, yeah. What you do is whatever x you have got, just pre-multiplied by this C matrix, yeah. So this is my C matrix, this is my B matrix, and this is my A matrix, and of course the D matrix is 0 here, there is no feed forward, as is often the case in systems, right, unless they are biproper, the feed forward will always be 0. So this is my goal, right, and I know from my other day, I mean probably a few lectures back we had derived this, right, that we have this, so we essentially have to look for this xs is equal to Si minus A inverse times this x naught, yeah. We already saw this the other day, isn't it, because we saw that if you take the Laplace transform on both sides, then you get Sxs minus x0 is equal to Axs plus Bus, right. This is what we generally get, and then we write that as Si minus A times Xs is equal to x0 plus Bus, and then we take the inverse on both sides and we get Si minus A inverse xs plus Si minus A inverse B us. Now if you want to get ys, which is nothing but C times xs, that is going to be just this C times Si minus A inverse. So we are assuming that there is no feed forward here, yeah, so we get C times Si minus A inverse, sorry, this is not going to be xs, this is going to be x naught, yeah, my bad. So likewise this is going to be x naught, yeah, x evaluated at time t is equal to 0 plus C times Si minus A inverse B times us. And now we already know that we have defined this as the 0 input response and this as the 0 state response. Like recall in the early days of this course when we were splitting up the response into two parts, now you see the meaning behind those names, right. And then we also saw, or rather we briefly touched upon the fact that you see this part here, this is comprised of two parts, right. So you know that multiplication in the Laplace domain is akin to convolution in the time domain, and this part, what is its Laplace inverse? We know that this is nothing but C e to the at, right. So then we have the y0 state in the time domain as C e to the at, and this star denotes the convolution with ut, which of course if you write in the according to the definition of convolution, then it becomes just C e to the power a t minus tau, sorry there was a b here as well, right, I forgot that b, excuse me, then b u tau d tau, yeah. So this is all there is to my 0 state response, okay. This is due to the forcing function that is coming in. If your initial conditions are all 0, then this is the only output you will see, alright. So we have already seen this, so now we want to translate this. So at the heart of all of this we find is the ability to get to this e to the at, because once we know e to the at, yeah, let us look at the x, this equation for the starters, yeah. If you look at this equation for instance, if you take the Laplace inverse of this, then you will see that xt is nothing but e to the at x naught, yeah, plus this integration 0 to t e to the a t minus tau b u tau d tau, right. So in both of these terms, the 0 input and the 0 state response, yeah, the 0 input response and the 0 state response, it is basically this e to the at that holds the key, and that is the reason why we have actually seen not one or two but just 3 exact methods to sort of at least get our way around or wrap our heads around how to obtain this e to the at, it is pivotal. Now in this particular example, it turns out that our A matrix is this 1 1 2 0 1 3 0 0 2, which we have seen the other day cannot be diagonalized, but nonetheless we can get this block diagonalized, yeah. Let me write that B matrix down once more at the cost of being repetitive, yeah. So the C is going to be 1 0 0, yeah, that is my system matrices, and of course D is equal to 0, right. So now I want to evaluate basically this is what I am trying to evaluate, because of course remember once I have evaluated this, getting y out of this is really not a big deal, you just pre-multiply by C and you pick out, in this particular case in fact you will just pick out x1, yeah. So once you have solved for, like once you have got this x1t, x2t, x3t, you have already done the hard job, right, the more difficult task. So this is some star, this is some star, and this is some star, and then what the C does is it is just in this case, because the C has the structure 1 0 0, it just picks out this. So this is going to be my output, yeah. So in this problem I will solve for this x, yeah, and there is another claim that I am going to make. I am not, yeah, notice please that I am not going to use Laplace transform at any stage. So the other day you remember when we took you to this diagonal form or this block Jordan form, right, and we got it to this diagonal form, and then we said how do you get from this diagonal form to the exponential of this diagonal form, yeah, and we took this Laplace inverse, right, because we said that once you have this T inverse AT is equal to this diagonal matrix, yeah, then you say that e to the T inverse AT is equal to e to the this diagonal. So how do you get the diagonal? We said that, well, you take Si minus this inverse and you take the Laplace inverse of this, yeah, and then you get this as some 1 by S minus lambda 1 dot 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 till 1 by S minus lambda n. These lambda 1 through lambda n could be distinct or repeated, I do not care, but the point is that now I can take the Laplace inverse of these n entries and I get e to the lambda 1 t dot 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 till e to the lambda n t. Now some of you might actually raise an objection and say, hey, you said that we will find a unique method for this, or rather a different method for solving the state space system without resorting to Laplace transform at all, but now here you have, although not very difficult, but you have still used Laplace transform to solve for this, right. So what could be a possible way out? Well, we already have defined this, remember, thus e to the at is going to be I plus at plus a squared t squared by factorial 2, so on and so forth. So a general term is like a to the k t to the k upon factorial k, infinite series. So why not use this, yeah. Once you have the diagonal form, notice that diagonal matrices, the multiplication is very easy, yeah. So if you take a diagonal matrix like lambda 1 lambda 2 dot 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 till lambda n and you multiply it with itself, yeah, k number of times like this, lambda n, you multiply this k number of times, yeah, k times, all that you will get at the end of it is lambda 1 to the power k dot 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 till lambda n to the power k, right. So now if you want to find out lambda to the power k upon factorial k, this summation of this series k running from 0 to n, or 0 to infinity in this case, sorry, it's an infinite series, remember, that's what the definition of this exponential was. Then what is this going to be equal to? This is going to be nothing but I plus, what is going to be each individual diagonal entry? It's going to be lambda 1 plus lambda 1 squared by factorial 2 plus dot 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 till lambda 1 to the k by factorial k, and an infinite series like this, the rest of the terms are going to be 0. Similarly, the last diagonal entry is going to be lambda n plus lambda n squared by factorial 2 and so on, right. So this is going to be equal to nothing but a typical diagonal entry, the off diagonal entries will all be 0, and a typical diagonal entry of this will look, let me take the first one, so it will be 1 plus lambda 1 plus lambda 1 squared by factorial 2 plus so on. The last fellow will be likewise 1 plus lambda n plus lambda n squared by factorial 2 so on, right. Then now we do not have to use any definition, we know that this is after all nothing but the classical scalar exponential series. So this is going to be e to the, sorry I missed the t to the k, did I? So let me put the t to the k here, t to the 0 here of course. So then there will be this lambda 1 t, lambda t squared, t to the k, yeah, t, and this is t squared. Similarly here will be a t, t squared, here will be a t, t squared. So this is nothing but e to the lambda 1 t, e to the lambda 2 t dot 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 e to the lambda n t, yeah. So notice that we arrive at, of course quite expectedly, at the same result, but the only difference here is that unlike in this part that I have written in blue, this, let me put it inside a blue box here, which is what I did the other day when I used Laplace transform, and you might not be very happy because this does not seem to be very much independent of Laplace transform. Now I have shown you that you do not need to resort to Laplace transform at all, right, because you know the exponential series of scalars, you can just write it like this, which gives you the same result as you obtained here through the Laplace transform route. So I hope that by now you are convinced that indeed we do not need to resort to Laplace transform at all. The state space method of solving ODEs or this system, solving for the solutions of this system, is basically independent of the Laplace transform method that you have learned earlier in this course. Okay, back to this particular numerical example. You might think I am digressing a lot, do I even intend to solve this, right? But I assure you that we will solve this by the end of this lecture at least, if not before. Alright, so now recall, in case you are noting down in the previous lecture, then you already have it before you, but if you do not, let me remind you that we found this matrix T given by 1 0 0 1 1 0. Remember that this matrix was not unique, 5 3 1, whereupon we also got T inverse given by 1 0 0 minus 1 1 0 minus 2 minus 3 1, okay, such that, so this we obtained already, so I am not going to go through that difficult task of evaluating those eigenvalues and the chains, right, the generalized eigenvalues therefrom, yeah, such that T inverse AT turned out to be this block Jordan form, which was 1 1 0 1 2 and this was 0 0 0 0, right. So this turned out to be my block Jordan form G, yeah, so far so good, okay. So therefore, from this A, using the similarity transformation, I found that although I cannot diagonalize this matrix, please refer to the other day's lecture on why we cannot diagonalize this, we have already shown it through computations, yeah, that you cannot diagonalize this, yeah, because there is a shortage of sufficient number of eigenvectors. In that sense, it is like a defective matrix. Some books or some places in the literature you might encounter the term defective matrix. Anyway, since this is not a course on linear algebra, we will not go too far with those terminologies. Right, now how far is this from a diagonal matrix really? What do I mean by that? Suppose I write this J as the sum of a diagonal matrix and something else. So notice that if I write it in this fashion, if I take out just the diagonal entries from here, what am I left with thereafter? What I will be left with is a very sparse matrix. By sparse matrix I mean that its entries are, most of its entries are going to be 0. In fact, here there is exactly one entry that is non-zero, every other entry is 0. So we call this N. So this is why I said how far are we from a diagonal matrix, because now I am going to call this J as a diagonal matrix, which I would have ideally liked this to be, but you know the Jordan form does not let me get to this exact diagonal form, but nevertheless it is close enough to this diagonal form. So I have this N matrix, this, yeah, that is somewhat like the party pooper, it is spoiling the party. So if it is spoiling the party, then can I get rid of it? Well, apparently on the face of it directly I cannot get rid of this, right, but maybe there is some special property or special feature of this matrix that will allow me to get rid of this after a point. Well, it turns out that this matrix is something that we call in linear algebraic parlance as a nilpotent matrix, which means that if you raise it to a sufficiently higher power, right, so there exists some r such that n to the power r will be equal to identically the 0 matrix, yeah. So that is a nilpotent matrix, yeah. So it turns out that this is a nilpotent matrix, and in fact in this case you will see that we get the 0 as soon as we get from this n to n squared, okay. So you just try this out, because there is only one non-zero entry here, it is going to be an easy job for you to sort of multiply this directly and see for yourself that as soon as you get from n to n squared, you get this n squared to be equal to exactly 0, alright. So how does that help, you might wonder? Well, here is another fact that we are not going to prove exhaustively or rigorously, because I will leave some gaps. Again, I will take the easy way out, the excuse is that this is an undergraduate course, so we really do not get into the details and nitty-gritties of everything. So here is a fact fact is, if matrices P and Q commute, that is PQ is equal to QP, yeah, then and only then, okay, let us forget about only then and only then, we just worry about one side, so let us not make it more complicated than it is, yeah. Then we have e to the p plus q is equal to e to the p times e to the q. Notice this is something very different from the usual conventional matrix, like usual conventional exponential function. In the conventional exponential function, we know that we have e to the x times e to the y, where of course x and y are scalars, yeah. Then we know that we can easily write them as e to the x plus y. That always holds true. But in case of matrix exponentials, in fact you can take it as an exercise, try cooking up two different 2 by 2 matrices and showing that e to the p plus q is not the same as e to the p times e to the q, yeah. Try cooking up one such pair of matrices and show that it is not necessarily the case that they will always commute. In fact, it turns out that if they commute, then you can safely assume that this relation holds, okay. Why is this true? Let us do a quick sort of, I am not going to do a detailed proof of this. Detailed proof would involve that showing that if you have two absolutely convergent series and then the product of those two series will also be absolutely convergent, okay. So we will not do that sort of a proof because that will take us really too far afield, but let us, whatever we understand the way we have defined this, in that sense let us do this. So this is going to be nothing but I plus p plus q plus p plus q squared by factorial 2 plus dot 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 till p plus q to the n upon factorial n, or let me write it r, let me not use n here, yeah, okay, this is a general term and this goes on till infinity, it is an infinite sum. Now the key to understanding this is focus on p plus q to the r upon factorial r, yeah. What is this p plus q to the r upon factorial r? Notice that this is going to be nothing because this commutes, so I can write that p to the a times q to the b, yeah, is nothing but q to the b times p to the a, yeah. To see that, you just see that p, write this a times, and then q, write this b times, yeah, and then swap this p and q. So you get p like this a minus 1 times, then you encounter a q, and then you get p, yeah, and then you get q like this q, and this is b minus 1 times. Now again with the next p fellow that it encounters, you swap like this. So likewise you will see that you will get this q right at the front, yeah, and similarly this p gets right at the back. So one by one, if you keep doing this operation, eventually you will get all the q's on the front and all the p's at the back. So that way we know that for any ab, any two integers, positive integers a and b, we have that p to the a times q to the b is equal to q to the b times p to the a, and therefore when we write this sum, because they commute, we can now use the binomial series, yeah, we can just use the binomial series. So we do not have to worry about we do not have to worry about writing p squared q and qp squared as really two different matrices. We can just write them as 2p squared q is equal to 2qp squared without any ambiguity, right. That is exactly what happens in case of scalars, right, when we have x squared y and y x squared, yeah, they are one and the same. So therefore when we write this as a binomial series, we can exactly treat this binomial series. So this is why that commutating property is important, that allows us to write this as a binomial series without worrying about the order in which, whether there is 3 p's then 1 q, then another 4 p's, then another 5 q's, yeah, in order. You put them in any order and you can permute and play around with them because they commute. So that is why commuting, that property of commuting between the two is very important, and therefore, so even though when I write this expression it is easy to miss, if I do not point it out to you, you might feel that why is that commuting part important. I can write this p plus q to the power r like p to the power summation like this, say, what should I say, k going from 0 to r, p to the power r upon factorial r, sorry, not r, p to the power k, yeah. So, this is exactly the binomial series times q to the power r minus k upon factorial r minus k, yeah, because remember it is basically r choose k. So, that is basically going to be factorial r by factorial k times factorial r minus k, alright. And now because I have divided it by factorial r, so this factorial r already goes this side, yeah. So, this is 1 by factorial k times factorial r minus k. So, now I can club these two together like this, yeah. So, each individual term like this will look like this, yeah, and because as I said this they commute, yeah, it does not really matter in what order. So, for example, let us take a short example, p plus q times p plus q. If you take this, if they do not commute, then you will have to write this as qp plus pq plus q squared, yeah. So, you will have to leave it at that, that is all you can do. But now if I say they commute, then I can additionally go to another step and I can write this as 2pq plus q squared, yeah. So, this is why then I can write this as a binomial series, right. This is exactly like a plus b whole squared is equal to a squared plus twice ab plus b squared, right. So, then we can treat it like a scalar. So, that is why that commuting part is important. I apologize if I am appearing to harp on this a bit too much, but this is really very important, that you do not mess this up and make the mistake of thinking that you take any two arbitrary matrices and you take e to the power p plus q, and that can always be written as e to the power p times e to the power q. It is not quite true unless they commute, okay. So, there we have it, right. Now, this is a sum, so therefore, can I not write this e to the power p plus q as a double summation now? See, one summation is coming because of this summation of each individual term contains a summation. So, let me be a little slow here. The first summation is coming here because I am going to sum over k going from 0 to r. So, this is k going from 0 to r, yeah. So, it is p to the power r by factorial r times q to the power, sorry, p to the power k by factorial k, excuse me, times q to the power r minus k by factorial r minus k, right. And the second sum will come because now look, this r, what is this r after all? This r is going from the 0th power to infinity. This r is just a typical entry, no, this r can go from 0, which is the identity, to 1, to 3, 2, 3, 4 like this till infinity. So, the second sum is r going from 0 to infinity, yeah, because remember what I have picked out here is just one of these terms. Now, I have got to sum these terms, right. So, I have got to sum this. So, that is where the second sum comes in, and that will only give me this e to the power p plus q, not before that will I get e to the power p plus q, and that sum is an infinite sum. Now, notice I am going to make an observation, yeah. The observation is, what is this after all tantamount to? If you give it a moment's thought, the first sum restricts the product to only those powers of p and q which sum up to r, but the second sum tells you that r could basically be any integer, right. Mark those two observations for me please. The first sum tells you that p to the power k, you take the product of p to the power k and q to the power r minus k such that the power to which p is raised and the power to which q is raised, their sum must be equal to r, yeah. So, it seems very restrictive there, but the second sum here tells you that this r could be anything from 0 to infinity. So, therefore, isn't this like I can take any power of p, say p to the power l upon factorial l, yeah, and I can multiply with it any power of, so l could be anything going from 0 to infinity, yeah, and m could be anything going from 0 to infinity as well, where this is q to the power m by factorial m, right. So now this, of course, from here on to the next step, what I am going to do, and this step as well, it requires basically some more sophistication. You cannot just always do this. In this case it works because these are basically series that actually are absolutely summable, yeah. So that is the only reason we are allowed to do this. In general we are not allowed to do this, okay, but we will not get into that. This is again, as I said, an undergraduate course. There is a limit to how rigorous we will get with this particular problem, right. So we will draw the line here. Now notice that where does this take us? So this will take us to what is this term after all? E to the p times e to the q, yeah. So therefore if they commute, at least I have shown you that this is true, but why is this important? Now cast your attention back here. What is this Jordan form? It is almost diagonal except for this one term which is spoiling the party. So therefore does this diagonal matrix, so my question is, do this diagonal matrix and the one that is spoiling this party commute? And the answer is an emphatic yes, they do. You check, for instance, in this case here, it will always commute, right. If you write it in the block Jordan form, it will always commute, because after all you can partition this conformally like this, yeah. So then if you multiply this j, this is the lambda and this is the n, right. So you multiply lambda times n, so lambda is the pre-multiplier, n is the post-multiplier. It is basically this block multiplying this block, then this block multiplying this block, and their sum. So this is basically 0, 0, 0, 0 product like this, so this is going to be 0, nothing new. When you multiply the 2, 2, so this is going to be like this multiplying with this and this multiplying with this, right. So that is again going to be 0. So finally, yeah, when you go for this block, then it is going to be this multiplying with this, which is a 0, and this multiplying with this, which is also going to be a 0, yeah. And lastly but not the least, you multiply this with this, sorry, with this. So this you multiply with this, which is a scalar 0, and this you multiply with this, you get a 0. So the only thing that remains is this first entry. So you take, for example, in this case, this times n, yeah, you will see that if you partition it conformally, these will be zeros quite trivially. The only thing that remains is, yeah, in this case the lambda is 1, so it is 1 times identity times n, yeah, so it is just going to be this n. So lambda times n, yeah, where this is in general lambda 1 times I and lambda 2 times I like this, yeah. That is how it is going to be, the diagonal structure. So this is going to be just this lambda 1. In this case, of course, the second one is not a, it is a trivial Jordan block, which is to say that it is a diagonal block, yeah. So this lambda 2 is just 1 by 1. So here it is just 1 by 1. So this is specific to this, but in general you can extend this idea and see that this is what you will get when you multiply. But what about n times this? Well, now you notice that you just reverse the order of multiplication, so this gets multiplied with this, but what is this? This is after all some lambda times identity. So again the 1, 1 block, this will be still the same, this will also be this lambda 1 times n, and you notice by a bit of calculations similar to before, yeah, this, so for instance this you multiply with, this you multiply with, I think this is moved a bit, anyway, so you understand the idea. The idea is that you multiply this now with this and you get 0, and then you multiply this with this, so that is your 1, 2 block, that will also be 0, yeah. So eventually you just take it as an exercise and you notice that this is not just true of this particular example we have taken, nothing special about this, it is going to be always true that this diagonal form in a block Jordan form or in a Jordan canonical decomposition, if you have got the matrix down to the Jordan canonical decomposition, you will always see that this diagonal block, if you split it up from this nilpotent part, yeah, they will always commute. And why is that important? precisely because if they commute, we know that this property holds. So therefore, e to the jt is going to be equal to e to the this, and because they commute, now we may write this as e to the lambda t times e to the nt. So this e to the lambda t is very simple, right? We just write e to the lambda 1 t like we usually write e to the lambda n t, irrespective of whether they are distinct or repeated, times e to the nt. Now what is so interesting or so simplifying about this e to the nt? Well, the nilpotence now shows its important role. So you see e to the nt is going to be nothing but I plus nt plus n squared t squared by factorial 2 plus dot 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 so on, right? But not really, it will never go to infinity. Why? Because we know that there exists some r, that is why it is nilpotent, there exists some r such that n to the power r is equal to 0. And once it is 0, then for every subsequent r, r plus 1, r plus 2 is going to remain 0, because remember this is a 0 matrix, yeah, an n cross n 0 matrix. So you multiply, pre or post multiply any other matrix with a 0 matrix, you will get a 0, right. So therefore, there will only be a finite number of terms here, and in fact in our particular example here, we have already seen that in this example n squared is equal to 0, in this example. So therefore, what is e to the jt? It is going to be e to the lambda t times e to the nt, which is going to be this e to the t in our case, because remember what was our Jordan block here, yeah, this is the diagonal part. So e to the t, e to the t, e to the 2t, those are the 3 diagonal entries, e to the t, e to the t, e to the 2t, times I plus nt, that is it, because n squared is 0, so I do not need to worry about the terms thereafter, right. So isn't that simplifying? Now what is this nt? You see e to the t, e to the t, e to the 2t, 0, 0 like this, and this is going to be nothing but 1, 1, and what is nt? We know the simple form of n, right. Let us go back, yeah. So this is our n matrix. So nt is just a t sitting in the 1/2th entry in the first row, second column, the rest all are going to be 0, yeah. So I am just going to have a t here, rest everything else is going to be 0, 0, 0, of course the identity will show its effect, so there will be a 1 here, the rest of the entries are going to be 0, right. So this is my exponential, right. So what do I get as e to the jt? E to the jt then turns out to be, well, let me see, I have probably computed this, so I am just going to write it one shot. You can take this up as an exercise and you will see that this turns out to be e to the t, t e to the t, e to the t, e to the 2t, 0, 0, 0, 0, 0, which is exactly as I had claimed it should look like, okay. So I have got the hard part of the task done, alright. So therefore, now I have that, given I had this original system which was x dot, yeah, is equal to ax plus bu, alright. So we had this x dot is equal to ax plus bu, y is equal to cx, of course the D matrix is not relevant here, right. So then what were we trying to do? By this similarity transformation, remember we transformed it to another variable, right. What was the other variable? Let us call it some x tilde, alright. So we will see now that we will actually solve this system of equations, this state space equation in the transformed variables, that is the x tilde, right, because if we do that, going from x to x tilde or the other way around is very simple, we already have a handle over this transformation, no. So that is what we are going to do, alright. So what is our next goal here? Here is how we set our goal. So we go for this ax plus bu, y is equal to cx, and therefore x tilde, so we define this x tilde as t inverse x, right, and then we saw that this x tilde dot is equal to t inverse a t x tilde plus t inverse b u, y is going to be equal to c t x tilde, right. So essentially now instead of solving this original system of equations, I can as well solve in this domain, in the x tilde domain. What do I need for that? What I need is, instead of x0, I now need x tilde 0, yeah. And now you might say, well, you might have solved in x tilde, but remember the original question had actually asked you for x, right. If you just wanted to solve for y, you would still get it. Just operate Ct upon x tilde and you will get the same y as in this system. It has to be, because they give the same transfer function, right. But if they ask you explicitly in the question to solve for x, then you give them as output like some function of t as x tilde, yeah, some 3 tuple. Then you have to again go back to xt from there, yeah. So first you go from x0 to x tilde 0 by applying this transformation T inverse, yeah, because I know that T inverse x is equal to x tilde, right. And then once you have gotten to this x tilde t, solve for the states in the transform domain, that is x tilde, then you better apply t on it back again. So then you get t x tilde is equal to x, yeah, and that is how you get the solution. So we will do exactly that. So now our goal is to first solve for x tilde t, which is going to be nothing but e to the jt, which is easy to evaluate as we have seen earlier, times x tilde 0 plus integration 0 to t e to the j t minus tau b. Of course there is a t inverse sitting here, because now remember this is my b, yeah, the b is this, yeah, so this is b tilde. So I have to write, let me write that cleanly, yeah, not like this ad hoc, in this ad hoc fashion. So this is t inverse b u tau d tau, where of course in the transform domain this is my 0 state response and this is my 0 input response, okay. So what do I need? Basically I need x tilde 0. So you check my calculations, I have already done it, so I am not going to repeat those calculations here. So I have calculated them, you check my calculations, this will also give you some good practice. So I found that x tilde 0 is equal to, upon operating this, you know, where was I? Yeah, so upon operating this, yeah, x tilde 0, upon operating with this t inverse here, this is what I will get. I will get x tilde 0 is given by I think 0 minus 3 1, yeah, probably that is what my, yeah, I think so, maybe if I am not too mistaken, yeah, that is going to be my x tilde 0, right, and my t inverse b is going to be 0 0 1, yeah. So now that I have all the variables that I want to evaluate, yeah, and plug in this equation, if I plug it in here, of course the e to the jt I already have, so this is known to me, remember this part, so this part I already know, this part I have evaluated, this part I have evaluated numerically, this part I know is just this step function, yeah, all I need to do is carry out a bit of an integration, yeah. So I have done that and I have computed it, I leave it to you as an exercise to check my calculation, actually that will be good practice, but yeah, I am not going to redo all this right here and reproduce it, okay. So what I then get is that this x tilde of t turns out to be, the first part will give me minus 3 e to the t times t, then minus 3 e to the t, and finally e to the 2t. So this is my 0 input response, plus if you do those integrations and carefully plug them in, you will get 0 0, because of this nice form that t inverse b gave me, yeah, these two terms will be 0, yeah, it is just term by term integration of this vector 3 tuple, yeah. So you will eventually end up with half e to the 2t minus half. So you sum them together, this is the 0 state, so you sum them together for the complete solution, which turns out to be, let me write that down here, minus 3 t e to the t minus 3 e to the t, yeah, and 3 by 2 e to the 2t, yeah, 3 by 2 e to the 2t minus half. Yeah, but I am not done yet, my job is not done yet, in the sense now I have to get to xt, which is going to be nothing but I have to operate t times x tilde t. Yeah. So again this t I had already evaluated, I had shown you what this t was explicitly several slides back, probably a few slides back. We have actually discussed quite a bit of theory in the process. By looking at this example, we have actually seen a bit of theory. So this is my T matrix, yeah, we had already obtained this in the previous lecture, as a matter of fact, not in today's lecture, yeah. So then I notice that this is going to be, let me make it very wide so I can accommodate this entire term, it is a pretty hefty sort of a term, it is minus 3 e to the t minus 3 e to the, just a minute, so then it is minus 3 e to the t minus 3 into t into e to the t, okay. So let me see, yeah, I think, and then what is there, hang on, let me see the computations here, yeah, minus 3 e to the t minus 3 t times e to the t plus 7.5 e to the 2t minus 2.5, yeah, that is one. So this is going to be my x1t, my x2t is going to be minus 3 e to the t plus 4.5 e to the 2t minus 1.5. So this is going to be my x2t, and finally x3t is going to be 1.5 e to the 2t minus 0.5. So this is my x3t, and as I promised to you earlier that once you have evaluated these states, getting the output is really not a big deal. So in my case my y is equal to 1 0 0 times x, yeah, so it is just going to pick out this first state as the output. So basically this is going to be then my output, right. So if that is my output, then I have actually solved for the entire system, right. So hopefully we managed to show you, in general things will be a lot simpler if this is a diagonal matrix, because if this was a diagonal matrix we would not have had to compute all those nilpotent matrices, right. Remember at this stage of the evaluation we had to multiply it by this I plus nt. If this was a diagonal matrix it would be just this I, so no nt. So generally the steps would be simpler, yeah, or it could be even more complicated if the Jordan block was even bigger, then you would have had to consider n squared maybe or n cubed maybe, but the guarantee is that at some point this is going to be a finite sum, yeah, e to the nt will not be an infinite sum unlike a general exponential because of the nilpotence of n. So that is the benefit of the Jordan form, okay. That is why we are so keen on this Jordan form and keen to understand what this Jordan form, its implications are in the long run, right. So hopefully we have enjoyed this lecture and you have learned something new about how to solve the state space method. Like I claimed in the other day, you might have been a little dissatisfied in the sense that we were still using some bits of Laplace transform, but today we have maintained purity of the turf, right. We have not used any Laplace transform, yeah, we have solved this independent of any method that you have learned hitherto. This is like the new method, a new paradigm that we have now shown you for obtaining solutions, okay. You might check using Laplace transforms and on the original equation, on original ODE, that is ordinary differential equation with the initial conditions that are given, that this is exactly the same solution you will get, provided I have not made any calculation mistakes here, yeah. So please do check, do practice. Although we took an entire lecture to solve this, I hope that you appreciate that this was not down to my poor calculating speed, it was also because we saw down the way a bit of the theory, right. We saw how to obtain the exponential matrix exponential for a Jordan form. So that is the reason why I took this example and not a simple example containing a diagonalizable A matrix, right. We also saw why when these exponential matrices, yeah, when they commute, these matrices commute, then their exponentials, sum of the exponential of the sum of those matrices is the product of the individual matrix exponentials. Yeah, so that commuting property is very important, and that we use to good effect to derive the result for Jordan form. Yeah, of course this is not a very rigorous proof. Again, I urge you to take this with a pinch of salt, not because it is wrong or anything, but because this is incomplete. This proof is really, if you want to get a completely rigorous proof of this, then that will be a bit beyond the scope of this course, alright. But I hope that for the purpose of convincing you that this is indeed correct and whatever we are doing here is right, yeah, this should be good enough. So in the next lecture we will address sort of kind of the elephant in the room around which we have tiptoed around a bit so far, in the sense that we have not really talked much about complex eigenvalues. Yeah, but in second order systems transient response we saw that you do end up with complex poles, and since every pole is definitely an eigenvalue of a system matrix of a state space representation, yeah, so therefore we should have some way of handling them. Yeah, if you want to find out the eigenvectors of such matrices with complex eigenvalues, then you have to admit complex eigenvectors too, even though the matrix is real, right. So we will see that in the next lecture, and followed by that the long promised, the long overdue discussions about a bit of linear time varying systems, right, which the state space method is capable of handling. So hopefully this should suffice for our discussions, but please I urge you to practice more and more of these problems in order to gain speed and accuracy. Yeah, because for 3x3 systems often you are asked questions, it's not really a big deal, everyone knows how to solve it, but unless you actually practice problems you will be stuck, you will be making some silly calculation mistakes, right. So please try to avoid that, yeah, and also practice on MATLAB, yeah, try learning some of the MATLAB commands for this, and that should hopefully get you interested even more into seeking solutions of these systems, even in cases where there are complex conjugate eigenvalues, repeated eigenvalues, all those cases. So far we have seen there are only real eigenvalues, repeated or otherwise, and in case of repetitions it may not be diagonalizable, the matrix A, in which case there is always this Jordan block, which is still somewhat simple to deal with compared to the original form of this arbitrary matrix. But now the next class quite logically will take us to the case of complex conjugate poles. Remember, the poles will only be appearing in complex conjugate pairs because the characteristic polynomial will contain coefficients from the system matrix, and therefore the coefficients of the characteristic polynomial will be real, and any polynomial with real coefficients must have complex roots in conjugate pairs. Yeah, because we are dealing with physical systems, all our parameters are real, and therefore the entries of the A matrix will be real. So therefore coefficients of the characteristic polynomial will be real, but that does not prevent eigenvalues or poles from being complex, but even if they do become complex, they will still appear in conjugate pairs, and that will hold the key, as we shall see in the next lecture. So until then, do take very good care.